Well, good afternoon. This is 12:26 actually now, on Wednesday, the 17th of October, 2018. It's supposed to be Calculus 3 class, and right now I'm the only one in the room. We're 11 minutes late getting started. I had a student come by my office right as I was finishing lunch and getting ready to come up here, and he had a problem. In fact, he's one of our students. Had a problem with financial services and had just gotten it straightened out, but he had to go to the Birmingham campus to deal with it, so he came by to tell me that. So hopefully he'll be back in class soon. And before that, another student come by to print a paper, and before that, it's just been crazy all morning. So sorry that I'm late getting started, but I did want to tell you, sorry, my throat's messed up. It has been just about all day. About a few minor changes to my office hours and one sort of big one. The minors are just temporary for this next week or so. Yesterday I had a doctor's appointment, and it took 3 hours from 9 to 12. I had to go get blood work and then the appointment and driving back and forth, all that kind of stuff. Added up to 3 hours. So I lost 45 minutes of my first class and all of my second class. So that's what the temporary changes are to my office hours. Tomorrow, and actually yesterday we did it too, we started 15 minutes earlier to make up 15 of those 45 minutes. We'll be starting 15 minutes early tomorrow morning, and we'll be starting 15 minutes early on Tuesday. So normally I'm in the office before 8 and up until close to 8:30, because that's when my classes start 4 days a week. But tomorrow and Tuesday, I'll actually be starting class at 8:15. So I won't be in the office much at all, a little before 8, and then I'll be leaving to set up and start my class before 8:15. All right, so that's the first change for that. That's tomorrow and Tuesday. After that, we'll be back to normal. My class I missed on yesterday, we're making up to, Friday, and normally I'm on the Birmingham campus on Friday mornings, but this Friday I'll be on this campus because I'll be making up that class, and that will be from 9 till 10:15. Now, if they need me to go into the Birmingham campus, I'll either go in before class and get done whatever I need to, or go after class and get done whatever I need to, or I may have to do both. So I don't know where I'll be the rest of the day. I'm hoping it'll be here on Bessemer, but if indeed they require me to go in to take care of some stuff, because there are some things that need taking care of, I may have to be back and forth between campuses. So that's Friday is kind of messed up too. Okay, the other, and this is for the rest of the term change, my first mini-term I had a physical science class that started at 1:15 in the afternoon, so my Tuesday, Thursday office hours were 11:15 to 1:15. Okay, the second mini-term, because there's automotive students in the class and they don't get out of their block schedule until 3, that means that we can't start that class until 3:15. So now my new office hours on Tuesday and Thursday afternoons are 11:15 until 3:15. So big 4 hours of office hours then, but that means I'll be here until 7:45 at night, probably 8 o'clock most nights. So on Tuesday, Thursday. So anyway, those are the changes that are happening. I wanted to let you know. All right. I kept thinking someone was going to come in while I was doing the talking, but no one has so far. So let's get started. Chapter 13 deals with functions of several variables. We've been in the first two sections of that. Today we're starting 13.3, which is partial derivatives. This, to me, is the meat of this chapter. The rest of it has been leading up to this. This is where we really start getting into the calculus of multivariable calculus, basically. Okay. Objectives here are to find and use partial derivatives as a function of two variables, find and use partial derivatives as a function of 3 or more variables, and find higher order partial derivatives of a function of 2 or 3 variables. So let's start with the simpler case with the partial derivatives of a function of 2 variables. you can determine the rate of change of a function f with respect to one of its several independent variables. Okay, so let's say, this will be sort of a dumb example, but let's say you're driving from here to Tuscaloosa. Okay? Now, what if you were, rather than just being a function of, say, speed, you also wanted to have it, and that's an independent variable, and the other independent variable would be something like, let's see, that may not be a great example. Let me think of something else. We'll run into examples of it. I thought I might have something right off the top of my head. But that process is called partial differentiation. If there's more than one independent variable, well, let's just say we have a curve here. Just picture some curve in space, okay? Now, it's curving one way with respect to the x-axis, but curving a different way with respect to the y-axis, okay? So the partial derivative with respect to the x-axis would be basically its slope on a plane parallel to the x-axis, whereas goes along parallel. I guess that's the best way to say it. Where its partial derivative with respect to where its slope with respect to the y-axis would be determined by a line or a plane that would cut through that curve that's parallel to the YZ plane. I guess that's a better way of saying it. Okay, that process is called partial differentiation, and the result is referred to as the partial derivative of f with respect to the chosen independent variable, whichever one you happen to be referring to. Okay, so here's your definition of partial derivatives of a function of two variables. If z is some function of x and y, that's sort of what I was describing to you before, then the first partial derivative of f with respect to x and y are the functions, and here are two ways of expressing them. They're showing one right here, f sub x. Let me get my pen reactivated. That's partial derivative with respect to x. This is partial derivative with respect to y. In a short time, they're going to show you another way to express this. This is the partial of f with respect to x. That would be this one. And partial of f with respect to y. That would be this one. Okay? The subscripts are sort of a shorthand. The others, they look a lot like a derivative, only we use that curly kind of a looking d. I'm not absolutely certain what that is anyway. I don't think it's a lowercase delta. It may be, but it's just another way of writing a d, but it indicates a partial derivative rather than the total derivative. Okay. So here's how we define the partial derivative of f with respect to x when it's actually a function of both x and y. Well, that would be the limit as delta x approaches 0, which would be indicated by this dx in the denominator, of f of x plus delta x. So since you're doing the partial with respect to x, you only vary the x. You leave the y alone, and that's going to be a key. Y doesn't change in this process. You're only changing x. So, but your function changes as you change your x a little bit, but don't change your y, minus f of xy. Notice the y hasn't changed, but the x has. It went from x to x plus delta x, divided by that delta x. That's how we define the partial with respect to x. And similarly, the partial with respect to y of a function still dependent on two variables, not one. Both of those are independent variables. Then you leave the x alone. The limit as delta y approaches 0 of f of x, comma, y plus delta y minus f of xy. Notice the x's are not changed. They stay the same. The y's are changed, and then you divide that by delta y, provided those limits exist. If the limits don't exist, there is no partial derivative with respect to that variable. But if they do exist, then that function with respect to that variable does have that partial. That definition indicates that if z is equal to f of xy, a function of both x and y are independent of each other, then to find f sub x, you consider the y as a constant and differentiate with respect to x. Just leave the y alone. Just count it as a constant. Similarly, to find f sub y, consider the x a constant, differentiate only with respect to y. Okay, here's the first example. Okay, and this is on the bottom half of page 894. And by the way, if you've got your books open, you see there's a little blurb there on Jean Laurent d'Alembert. Okay, obviously a French-sounding name. Lived from 1777 to 1783. So just to give you a little perspective, of course he didn't live that long. That's 66 years, which is not bad for that time, that age. Okay, but that was before the French Revolution. This is when, frankly, France was probably the top nation in the world at this time. This is in the Louis the 14th and 12th, that time frame. France was riding high. They were really, they had the money, they had the art, they had the science, they had the math. They were really the honcho country on earth. Okay, at least earth as the Europeans knew it. The Chinese may have been doing great things halfway around the world, but they weren't aware of it. Okay, so the introduction to partial derivatives followed Newton's and Leibniz's work in calculus by several years. And between 1730 and 1760, Leonard Euler and Jean-Laurent d'Alembert separately published several papers on dynamics, in which they established much of the theory of partial derivatives. Those papers used functions of two or more variables to study problems involving equilibrium, fluid motion, vibrating strings, that kind of stuff. And you can read more. So there were umpteen paper topics right there. Newton, Leibniz, Euler, d'Alembert, of course. Hey, it's good to have a student here. All right. Actually, one student did come by earlier, but he had to go to the Birmingham campus to take care of some business. He wasn't sure if he'd be back. He didn't sound like he thought he'd make it back, but glad you're here. Okay. I've already started, so what you'll need to be doing is playing a little catch-up or mustard, either one. So we'll see what we can do from there. Okay. Take a little bit for the screen to come on. I was just talking about the blurb on the side of the page from d'Alembert, and I think you've already turned in the paper, right? I have. Okay. So for the others who haven't, that was even more appropriate. But those people they could choose, but then also the calculus of dynamics, the equilibrium, calculus dealing with equilibrium problems, fluid motion, vibrating strings, all those would be potential paper topics you could get from that one little blurb. Now that can't be your source. You need to go elsewhere to get the source, but this gives you ideas for what to do. So we're ready to do example 1. Now, I've already done the top part of the page, so you have to go back and listen to that, but let's pick up and go from here. Now, what this f sub x stands for, that's a shorthand notation for the partial derivative of this function f with respect to that variable x. Now notice f is a function of two independent variables, x and y. Okay? And this is what this chapter is all about. When you have functions that have more than one independent variable. First two sections have dealt with limits and continuity and all those kinds of things. Now we're getting into derivatives. So to me, this is the real calculus of it. The rest we had to have, this is the real calculus in my mind. Okay? So what we're doing is taking the partial of this function f only with respect to the variable x. What does that mean we do with y? You treat it as if it's a constant. You don't mess with it. You don't change it. You just consider it to be a constant and differentiate only with respect to x. Okay? So, the partial of f with respect to x is still going to be a function of x and y. What would that be? Take the derivative with respect to x. 3 minus. Now, that next term, you're taking the partial with respect to x, but treating y as if it's a constant. Okay? So don't try to differentiate the y, but just treat it as a constant. So what would that be? Minus 2x, and then just treat the y as if it's a constant. 2xy squared. Don't mess with it, don't throw it away, don't leave it, but just treat it as if it's a constant. Okay? That's the second term. How about the next one? Plus 6 yeah, 6x squared y. Yeah, just write down the y. Bring down the y. Treat it as if it's a constant. Okay? There it is. You just took your first partial derivative, right? Good deal. Did it well, too. Okay? Now, I guess that's all there was to that. Let's see if the yak is in the way, so let me erase mine. Okay? So there they wrote down the function. No, they actually took the derivative. 3 minus 2xy squared plus 6x squared y. Just what we got, right? All right. Let's see, that was an A. Let's see if there's a B. To find f sub y, okay, consider x to be the constant and differentiate with respect to y. So what would be your f sub y of xy? Now, we're not doing it of this function. We're going back to the original function. So what would that be? That, remember, x is treated as a constant. And what's the derivative of a constant? 0. So, you see, as long as there was x in there, then you could derivative, and then your y's hung around. But if there's no y's in there, derivative of that constant is 0. So that one contributes nothing. Then you have a minus partial with respect to y.
Minus
2. The x squared, you keep them. They treat those as a constant. Y. Because there's a y in there, you don't throw away your constants, you keep the constants. Right? Okay. Next. Plus. And stop there, because the derivative of y is 1. So there is no y left in there. There's your partial with respect to y. Okay? Because you treat x as a constant and there's no y's in there, the derivative of a constant is 0 with respect to y. Okay? Because x is a constant, treat that as if that was 17. Whatever constant you want it to be, the 2 times the x squared times the y. Drop that by 1. Okay? And then the last one, keep the x squared cubed just as if it's a constant. Okay? And it'd be 2x cubed, and the derivative of y is 1. See it? All right.
So when we're doing f of y, we'll treat the x as a constant.
Say that one more time.
When we're distributing f of y, we'll treat the x as a constant.
Okay, when you're doing f sub y, you treat x as a constant. When you do f sub x, you treat y as a constant. Exactly. Exactly. Okay? Very good. Now, what they left off here is this is b. That was the b part of the problem. They just didn't put the b in there. Okay? No, I'm sorry. That was all part of a. Sorry about that. Sorry about that. Not there. Okay. The b part is different functions. Let's see how they did the second part. Okay, f sub y would then be, the first term has no y in it, so its derivative is 0. The second term has a y squared, so it's a minus 2y, or 2x squared y. And the third term, because it has y only to the first power, is just its coefficient, which was 2x cubed. Okay? Because you treat x as if it's a constant. Okay. Now, the b part is doing a different function. Sorry. Find f of x for f. They left off the f here. They keep leaving off something. For f of xy equal to log x sine x squared y. Okay? So what we want is f sub x then. It's also a function of x and y. Okay? Now, what do you have to do when you're taking a derivative of that kind of an expression? What rule do you have to use? What does this thing in parentheses written next to that thing in parentheses indicate? What arithmetic operation? Okay, yeah. Don't take a derivative yet. Just what does it mean for this to be in parentheses next to that in parentheses? What operation does that indicate? Multiplication. And what's the answer in the multiplication problem? Sorry? Yeah, what's the answer called? When you multiply two entities together. The multiplicand, multiplier, what's the answer called? The result of something you produced is called the product. This is the product of two entities. Okay. So what rule would we be using? The product rule, of course, because both of these have x's in them, right? Okay. So how does the product rule go?
Time to first.
The what?
Time to first, right?
Okay, no, wait, wait. Okay, now we're taking a derivative. Now we're doing the f sub x. So we use the product rule to take that. And how does the product rule go? Okay, something like that, but not that.
Yeah. I'm trying to get it together. I know you multiply.
Okay, what are we doing? Taking a derivative.
Taking a derivative.
So you multiply what?
Multiply sine and the log.
Okay, you're going back to multiplying again. That, you can't really do any more to it than multiply it and write it next to each other, because those are different functions. Okay? There's no sums or differences or anything else. They're just two functions multiplied together. What we're asking now is how to take a derivative of the product of two functions. Remember the product rule? How does it go? Now, there's one of two ways you can say it. You choose which way you like. It's either the first times the derivative of the second, plus the second times the derivative of the first, or the derivative of the first times the second, plus the derivative of the second times the first. It doesn't matter. You just got to do two and add them together, but you exchange which one you take the derivative of. So, which way you want to do this one?
I guess.
The first, so you're going to take the first, so that's just going to be log x. I can't write, times
You're taking a
derivative of the second then.
Yeah.
Okay, and what's the derivative of sine? Cosine of x squared y. But this is a composite function, so you need to do a chain rule, so that's got another product in it, and what is it? Y. Count the y as a constant. 2xy. Okay? There's the first times the derivative of the second. Plus yeah, x squared y, just write that down as it is, times the derivative of the first. And what's that? Derivative of log x. Natural log x. Second? No. Derivative of 1/2 x squared would be x. No, derivative of x would be 1. No, derivative of constant would be 0. That last chapter we did derivative of log x. It was a long time ago, I know. Derivative of log x is 1/x. Derivative of log x is 1/x, or x to the minus 1. Okay? It was earlier, I think. Okay? No. I'm sorry. I was thinking the last class. Oh, this was back in Cal 2 we did it. I'm sorry. My last class, which was Cal 2, we did it last week. Yeah. I was thinking it was this class we did it last week. No. So that's it. Okay? Now we can clean this up just a little bit. I tend to put this part in front. 2xy times log x times cosine x squared y plus sine x squared y over x. Not much you can do to simplify it, but there it is. Okay? The product rule is first times the root of the second plus the second times the root of the first. Okay? But the second one had a composite function, so you had to do a chain rule on it. Okay, so it was derivative of sine is cosine of x squared y, but then you do a derivative of the inside, which is 2xy. Okay. And I think I'm going to have to erase this, so let me erase it. But you remember what our answer is, and we'll compare how they did it with what we did. So f sub x of xy would be, they took the first, lifted along, times the derivative of the second, and the second derivative of sine is cosine x squared y, chain rule times 2xy, just like we did, plus the sine of x squared y over x. The second times the root of the first. The root of log x is 1/x. And I think that's how they leave it. Let's see if they manipulate it any. No. Okay. Now let's find f sub y of that same function up there. Okay. So what would be your f sub y? Okay. F sub y. xy. Okay. 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 Now, what are you doing? Explain to me what you're doing.
You were taking a derivative
Of that thing with respect to y.
Yeah. So f of y.
Say again?
F of y, right?
Yeah. That is your f of y. Take the root of that with respect to y.
So once you set it up as f of y is log x times cosine.
Okay, that's right. Log x times cosine. I didn't hear that before. Cosine of what? X squared y. Times x squared. Right. Done? Yes. Because you see this log x has no y in it, so you don't have a product rule anymore. You just treat that x as a constant, so log x is a constant. So that's just treated as a constant, the coefficient of this. So you just take the derivative of the sine x with respect to y, and it'd be cosine x squared y times your x squared. Now, just because of the way I like to do things, I would rewrite that as x squared log x times cosine x squared y. Just because I'm afraid that someone might think that this is part of what you're taking the cosine on. It's not, so I put it out front, so it's obviously it's by itself. But you don't have to. And I bet you, let me erase what I've got, I bet you they leave it just like the first line was there. Let's see. So L sub y of that would be log x cosine of x squared y times x squared. Now, I think that's exactly how they, that's exactly how they left it. And it's fine. It's perfectly fine with those parentheses there. That keeps it clear. Okay? All right. Any questions on those? Okay. So here's some notation issues. Okay? And this is what I was describing before. Okay? I only did part of it because they're introducing another thing. Let's say z is your dependent variable, and f of xy, these are your two independent variables. F is a function of two independent variables and has one dependent variable for its result. So the partial derivatives, we already exposed ourselves to f sub x. It's partial of this f with respect to the first variable, and this is f sub y, the partial of f with respect to the second variable. We can also denote that by this squirrely looking little d, a crooked little d. That means partial with respect to x of f of xy, which is the same as f sub x of xy, which I was using that notation. The other way you can say is z sub x, just like you said f sub x, because f is z, okay. Or you could just say partial z with respect to x. Or you could leave off this and just say partial of f with respect to x. That's one more way you could express it. Okay? Now, they tend not to do that, but you could. Partial of f with respect to x. Same thing. You understand f is a function of x and y. Okay? And then the partial with respect to y of f of xy. That's what before they were calling f sub y. Second one there, f sub y. And that's f sub y of xy, which is what I was writing. They didn't write it that way before, but I did. And then you could call that z sub y, partial z with respect to y only, or partial z with respect to y. That would be fine too. And the one other way that is legitimate, they probably don't like to, but you could just call this partial of f with respect to y, assuming that everybody realizes that f is a function of both x and y. So you don't have to write that. Now, what if you were evaluating this partial at some point AB? Now here, when you're giving a point, okay, remember your Z is a surface. Some sort of surface here. You're doing all sorts of things here over the XY plane. So to give an input here, you need to send some value of X and some value of Y. Those are independent of each other. That gives you one and only one Z value. Okay? So then if you're wanting to evaluate this partial of Z with respect to Y, with respect to X, if that's the X-axis, that would be some line or plane or something like this, okay? At one particular point, X equal A, Y is equal to B, okay? If you want this evaluated at some point, Before, when we did regular derivatives, all you needed was x equals something, because it was dy dx. But now you have a dz, partial z with respect to x with y constant, and partial, okay. So what you do then is take the partial of z with respect to x, that's your f sub x, that's just another way of saying it, and then evaluate that at AB. Now you didn't change the b part at all, you changed the x, but you still evaluate it at A. Or the partial with respect to y of AB, you take the partial with respect to y, and then evaluate it at that point AB. Just like we used to take the derivative with respect to x and then evaluate it at some value of x. Now it's some values x and y. Okay. Now, it looks like to me they've skipped example 2. Let me make sure. Yeah, they skipped example 2 completely. So let me go back and find. Okay. We'll do example 2 here. For f of xy to be equal to x e to the x squared y, find f sub x and f sub y and evaluate each at the point one log 2. That's a weird point, isn't it? All right. Now, I'm a cynic, okay? So I always like to check and make sure that point is really on this curve. So let's see what happens. When you put a 1 in for the x, okay? Well, you can't really tell. 1 in for x, and we'll put 2 in, no, log 2 in for y. So you put 1 in for x, you get e to the y, right? Because x is 1. But instead of y, we put in log 2, e to the log 2. Remember, e undoes a log undoes an e. It's just the number 2. So this value is 2, okay? Now, we have no way of checking that. They didn't tell us that. But that is the point. That's your x, y, independent numbers. They don't depend on one another. But when you do that, your z value is equal to 2. Your f value is equal to 2. But what they want us to do is find f sub x, and then we'll evaluate that at 1 log 2 as well. So how do you get f sub x? Okay. Now, what are you doing? What rule are you using? Product rule, because it's this function is a product of x and e to the x squared y. That's a product. When you write them next to each other, that means a product. So how does that product rule work? What times the first?
You'll have x.
Okay, x times, okay, derivative of this, which is e to the x squared y, derivative of exponential is itself, but this has a composite function, so you need to do a chain rule, and the chain rule gives you
2x
y. Perfect. Okay, so there's the first times the derivative of the second. We'll come back and work with that a little bit later. What's the second part of the product rule? Plus e to the x squared y. Perfect, because it's the derivative of the first, which is just 1, times the second. So that's it. Now, there's a little bit we need to do to the first part here. See, we got something multiplied here and something multiplied over there. You can multiply those two together. So I would make it 2x squared y e to the x squared y. You see that? Combine these two together. Okay? That would be 2x squared y e to the x squared y plus e to the x squared y. Now, since we went that far, you could factor out the e to the x squared y, because that's common for both terms. That'd be 2x squared plus 1. You don't have to do that. That's just another way to write it. Okay? No better, no worse, just another way to write it. Okay? So there's your partial with respect to x. In two different forms. Three different forms, actually. Okay? Let's see if we could do the partial with respect to y on the right-hand side of this. So your f sub y of xy would be what?
Taking the y, right?
Yeah, partial with respect to y. Okay, x, x is just as it's a coefficient. E, and you're taking the derivative of e, and that's itself, x squared y. But now you take, chain rule, the partial with respect, the derivative with respect to y. And what would that be? Of this part up here. I'm sorry, this part up here. Derivative of that would be, with respect to y?
Oh, it'd be x
Squared, just x squared. Okay, because you're taking the derivative with respect to y, so the y disappears. Right? Derivative of 7y would be 7. Derivative of x squared y would be x squared. Right? All right, now we can clean that up a little bit, and that would be x cubed e to the x squared y. Okay, there's your partial of f with respect to y. Now we need to evaluate each of these at the value x equal 1, y equal log 2. So f sub x at 1 log 2 would be what? I don't know which form you like better. I kind of like that one. So let's plug in x equal 1. So that would be 1 squared is 1. And y is log 2. So you have e to the log 2 is simply 2, right? Times 2 plus 1 is 3. So that looks like a 6 to me. Pretty simple, huh? Okay. Now, let's see what we get over here. F sub y evaluated at 1 log 2. Okay. And let's do of that form over there. Your x is 1. So y cubed is 1 times e to the 1 times log 2. That would be simply 2. Right? You plug in the 1 for x. 1 cubed is 1. E to the 1 squared is 1. Log 2. So e to the log 2 is 2. See it?
When you said plug in, you going back to okay, I see.
Yeah. For x you put the 1, and for y you put the log 2. So you put 1 in here, 1 cubed is 1. E to the 1 squared is 1. So e to the y is log 2. So since x and x squared is 1, e to the log 2, that's just 1 times 2. All right, now that's what I got. Let's see what the book got. Uh-oh. We got different answers. I must have messed something up pretty badly here. Let's see. F sub x is equal to x e to the x squared 2xy, we got that right. Plus that, yeah, got it right. The partial derivative of f with respect to x at that point would then be I think I did mess something up here. This has a y in it. I missed that. When I pulled out the x squared y here, e to the x squared y here, it was left with 2x squared y plus 1. I forgot the y. Okay? So let's go back and adjust our answer then. Okay. See, they didn't take it that far, and I shouldn't have. Okay. So let's see what we get when we plug in. X is equal to 1, y is equal to log 2. So that's just going to be a 2. This is going to be 2 times 1 is 2. So it's times 2 log 2 plus 1. Okay. So when you multiply that through, you get 4 log 2 plus 2. And that's what they got. Got it. Okay, and on the second part, we got it right. It's x cubed e to the x squared y, which would be, when we evaluate it, that would be e log 2, and e log 2 would just be 2. Okay. Now, that was example 2. Let's move on to the writing underneath example 2. And that leads to this. The partial derivatives of a function. Partial derivatives of a function of two variables, z is equal to f of xy, that's that red curve, that red surface up there, have a useful geometric interpretation. If y is equal to y0, in other words, you're somewhere here, come out y0 on the y-axis, and that plane would be any where y is equal to y0. Then z would be some f of x0. You see, z on this thing, this only has x dependence. It has no y dependence because the y is fixed at y0 there. Okay? If y is equal to y0, then z is equal to f of x y0 is just going to be this curve right here. Okay? Represents the curve formed by intersecting the surface of z is equal to f of x y, that's the red curve here, with the plane y equal y0, and you get this curve right here, this black curve there. Okay? Now, your partial of f with respect to x is your slope in the x direction. Now this, to me, at that point there, looks to be a downward slope, so that would be some negative value. If it were over here, that might have a slight upward slope, okay? So that would have a positive value. There's someplace there, probably right in here somewhere, where it has a zero slope with respect to the x-axis, okay? So that would be the slope in the x direction, okay? Looks like to me that slope's a little, that may be the 0 point, I don't know. If this is parallel to that, that would be. Looks like to me that's tilting down a little bit more, but it's not much. Okay. That's the trouble with trying to represent a three-dimensional shape on a two-dimensional board. It's really hard to do. All right, so therefore, f sub x at x0, y0 would then be the limit as delta x approaches 0 of alpha of x0 plus delta x, y0 minus alpha of x0, y0. It represents the slope of the curve at that point, x0, y0, and f of x0, y0. In other words, use z0. Note that both the curve and the tangent line in the plane note that both the curve and the tangent line lie in the plane y is equal to y0. Yeah, that's how we picked it out. That curve and its tangent line are in that plane y is equal to y0. Okay. All right. Similarly, if you were going to take the partial with respect to y at a point x0, y0, well, partial with respect to y is already holding x constant, so that would be constant at x0. So let's say this plane is some, you come out the x-axis some distance from the y-axis. It's not very far, just a little bit out here in this illustration. But you come this way, well, that plane where it intersects that same curve, that's somewhere along there. There's the line that intersects that plane, the curve intersecting this plane here, okay? And this is parallel to the y-axis, okay? Because you've got x0, x is fixed, and so this line is parallel to the y-axis. Now this is obviously going downhill from here, okay? So that would be a negative slope. Somewhere back up here, it would be a positive slope. And somewhere in between, you would have a place where it's zero slope. Okay, that represents the slope of the curve. This y, f sub y, x0, y0. The limit is the delta y0. Delta y is approaching 0. F of x0, that doesn't change in either one of these, comma, y0 plus delta y minus f of x0, y0, without a plus delta y in it. Then divide by delta y, and that gives your f sub y. Okay? So, there you have it. And there's a figure that represents it. So that would represent the slope of a line parallel to the y-axis, the slope with respect to y. Okay? At some fixed value of x0. Okay. Informally, this is the bottom of the page, 895 here. Informally, the values of partial of alpha with respect to x and the partial of alpha with respect to y at some point x0, y0, z0 denote the slopes of the surface in the x direction and the slope of the surface in the y direction. Both of these are partials with respect to, first is with respect to x, the other is with respect to y. Okay? You're taking the partials of the z, that's where the z comes from. You can substitute partial of z with respect to x, partial of z with respect to y at these 3 points. Could say it that way. Now, why do they have the z0 there? Why is that a variable? Well, once you figured out what the x0 is and the y0 is, you've got one and only one z0. So that's what that is. That's just the point at which you evaluate it. Okay. And that's the end there. Here's example 3. Now, example 3 is also found at larsoncalculus.com for an interactive version of this type of an example. So it may not be exactly like this, but it'll be something similar. Most of the time it should be pretty close to the same. Find the slopes in the x direction and in the y direction of the surface f of xy is equal to minus x squared over 2 minus y squared plus x 25 eighths. Okay? At the point 1/2, 1, and 2. Okay? And again, the cynic that I am, I want to verify that point is indeed on that curve. Okay? So this represents the x value. So that's going to be 1/2 squared, which would be 1/4, divided by 2 would be 1/8, And with a minus sign, that would be a minus 1/8. Minus 1, so minus 1/8 minus 1 would be minus 9/8, okay, plus 25/8. 9/8 plus 25/8 would be 16/8. That's 2. The z value, which is what alpha of xy is 2. So sure enough, there's the point. And that point is on that curve. See that? Now, oh man. So what does it say do? Find the slopes in the x direction and in the y direction of that surface at that point. Okay? So, slopes in the x direction, what would that be? Second? You may have said it right. F sub x of xy. We'll do it of xy first, then we'll come back and put 1/2 1 in there. Okay? So this will be what? Let's take the partial of that with respect to x. Okay, say that again. X? Negative x. Is that what you said? Yeah, exactly. The partial of that with respect to x is negative 2 times 1/2. That would be a negative 1 times x. Right. Next term? Yeah, but that's, you count it as a constant if you're taking partial with respect to x. So that would be 0 and that would be 0. So this is your f sub x of xy is negative x. Okay? So let's take that f sub x when x is equal to 1/2, y is equal to 1. And basically I'm going to stop there because this is a point. Your f is only a function of x and y. Okay? So when you plug that in, what do you get? Negative 1/2, right? Yeah. You just plug in the x, which is 1/2 for there, be a negative 1/2. Okay? Now, goodness gracious. What I did, this is partly my fault, I think. I crammed down lunch as fast as I could, which was probably in 20 minutes. And that's a bit too fast. And I wound up not drinking enough fluid while I was eating my lunch. So I think now I'm dry, totally dry. But it's all beginning to act. Okay. All right. That was our f sub x. And so this is the slope. So this is the slope of the function at that point in the x direction. Negative 1/2, yeah, wherever that is. Okay, let's do the same for the y direction. That would be f sub y at xy. We'll first do it at the variables xy, and then we'll come back and plug in the value. What would be f sub y of xy? Where do you get that?
Well, I'm just plugging in what the x and y is supposed to be. So
no, don't do it yet.
all right.
Do it the partial. Take the partial of this first at x and y. Once you get the partial, then when you plug in. See, if you plug in now, it's going to be a constant, and the partial will be 0. Okay, you lose all meaning. So take the derivative with respect to the variable, and then plug in what the value of the variable is. So what is f sub y of that thing up there?
2y.
Okay, minus 2y. Yeah, minus 2y. The reason is this term has no y in it. So you treat x as if it's a constant, so that's a constant. Derivative of a constant is 0. Derivative of this with respect to y would be a minus 2y. That's what you get. derivative of a constant is 0. Okay, so that's all you got. Now we plug in those values, f sub y at 1/2, 1, and which is the only value that has a meaning there? Yeah, that would be 2. The answer would be, well, actually minus 2, right? Because the minus 2y, and you plug in, you don't have any x's here, so there's nothing to plug the 1/2 in, so plug a 1 in there, minus 2 times 1 is minus 2. So in the y direction, so let's see if we can use the 4. So you have some curve here in the space, and at the point 1/2 in the x, 1 in the y, that's going to give us a 2 in the z direction. At this point here, when you go in the x direction only, the slope is minus 1/2, slightly down. When you go in the y direction at the same point, it's minus 2, much steeper down. So this is a curve that's falling out in both directions, slightly in that direction, pretty drastically in that direction. That's what that curve is doing at that point. 2 is the z value at that point. Okay? Does that kind of make sense?
Yeah.
Okay. So let me erase this so that we can write here. The partial derivative of f with respect to x and y are, just like we did, that was the minus x, and that was the minus 2. We did them separately. That's what we got. Always take the partial with respect to the variables, then plug in the values of the variable. So now we plug, now we plug in the negative 1, or 1/2 1, you get negative 1/2. When you plug in 1/2 1 for the partial with respect to y, you simply get a minus 2. Okay? And here's what that's showing. In this direction, when y is equal to 1, so come out 1 unit on the y, there's that plane, y is equal to 1. That gives you this part of it. Okay, your slope of that curve that's made with this shape, that plane, is at a negative 1/2. Frankly, to me, that looks a little too steep for negative 1/2, but it's okay. I can't draw it any better, so we'll take that. But if you make the plane at x equal 1/2, so that's back here, there's 1, 2, 3, so x equal 1/2. That's here, you see there's 0 and 1, and 1/2 is halfway in between those. Okay, and you do that plane, x equal 1/2 of the same curve. Now you got a really steep negative slope, negative 2 for your y. So now you're parallel to the y-axis, and you're counting how much fall off through is there. Now, I don't know why this sort of flashed in my mind, but it did. You can almost picture this as being kind of a stocking cap and say rain is falling on it. Well, here where it has your forehead is coming off at a slight angle, but on the side of your head here is coming off at a very steep angle. So that's why it's coming off slightly that way, very negative that way. That's a weird stocking cap.
Right. Very odd.
Thank you so much. Okay. All right. Strange example. Okay. And I think that's all of example 3. Okay? Oh, you still good? Huh? You are? Okay. All right. Let's see if they got example 4 in here. No, they don't. 4 or 5. So let's go back. Let's do 4 here. Looks like that's where we got the most room. Find the slopes of the surface f of xy is equal to 1 minus x minus 1 squared. Oh, the 10 o'clock scholar, why do you come so soon? Okay. Jeremy's here. Okay. Boy, attendance this week is up from Monday. When nobody was here, okay? At least we got 2 people here today. Actually, the third person came by earlier, but he's still trying to work out something with financial aid, and so he had to go to the Birmingham campus. He said he might not be here today, so he'll be here Monday. He was in the class, he was removed from the class, he got back in the class, then they removed him from the class, and now he's back in the class, I guess. I don't know. It sounds like revolving doors there. Okay? We're doing example 4, which is at the bottom of page 896. It's not on the slide set, so that's why I was doing it here. Minus y minus 2 squared. Okay. Now, you probably don't recognize this, but if I were to put a z here and then move these over here, that would be a x minus 1 squared plus y minus 2 squared plus z is equal to 1. Now, from our studies back in, what was it, 11.6, when we did the quadrant surfaces, when you have z to the first power and the other 2 to the second power, that's usually a paraboloid. And since those 2 have the same signs, that would then be an ellipse. Just those 2 by itself, forget about the z. So this would be an elliptic paraboloid. Because one's written in a strange place. Because these 2 themselves form ellipses, okay, but not centered at the axis, z-axis, centered at 1, 2. So you've got a horizontal shift for both of those, 1 on the x-axis and 2 on the y-axis. So that's the center of it, and then the z is 1 minus that. So this is an elliptic paraboloid centered at the place 1, 2. X equal 1 and y is equal to 2. Okay? And if you look at the one in the book, you can see that is an elliptic paraboloid. The only trouble with it is it's opening downward. Yeah, that would have to be. Because for most values, x's and y's, where the x is positive or negative, this thing is positive, this thing is positive. But then you're subtracting those, so the odds are for most of the time z is going to be negative. So therefore it will be a negative. All right. Who cares what it is, though? Okay. It says find the slopes of the surface, that surface, at the point 1, 2, 1. And again, I'm a cynic. And I want to make sure that is on the surface. So we put x in, 1 in for x, this becomes 0. So that's 0. 2 in for y, that's 0. And guess what? Z is equal to 1. Yes, that's it. And looking at the graph in the book, that's also your vertex of that elliptic paraboloid. That's the highest point. Everything after that is going downhill. Okay? When z is equal to 0, then you have this squared plus this squared equal 1. That would be an ellipse, you know. centered here, but yeah, like that.
So if it was they had a Z somewhere.
What's that?
They had a Z on this.
Okay, your f of x, y is your z.
Like at the bottom, where it say, so at the point 1, 2, 1, the slope direction, x direction is, you got fx 1, 2, and y 1, 2.
Okay.
And
all right.
It would have a, like if it was a z, like if it said z minus 2 squared, like at the end, would you have to put a z? Would it be fz at the bottom?
Okay. Here's something I think you're asking. See, f is a function of only x and y. X and y are independent variables. The f itself is the z value. That's your dependent variable. So the f is the z. Okay. That's a point in 3 space. Independent x, independent y, dependent z. So the z there, okay. You only have 2 variables here because there's only 2 independent variables. But this is your third variable, but it's dependent. Yeah, it's kind of by itself. But you know, when you talk about y as a function of x, right? A curve in space and on the xy plane, okay? Any point is still xy. X is independent, y is dependent. Here you have 2 independents and 1 dependent. So a point will have 3 coordinates, but your function is only a function of the 2 independent variables. Is that what you were getting at?
Yeah.
Okay, yeah. Okay. Yeah, that's what I thought you probably were doing. Okay. So, we want find the slopes of the surface, there's the surface, at that point, there's the point, okay, in the x and y directions, x direction and the y direction. So what's the slope in the x direction? How would we get that? The partial derivative with respect to x, okay? And we first do it xy, okay? You always take the partial with the variables xy, then you plug in the 1, 2, okay? But take the partial this way. So what's the partial of that curve, that surface with respect to x? -2. Is that all? I believe so. I have a problem here, though. No, it's -2x, right? Well,
Yeah, so you plug
okay.
in the x.
Yeah. Okay.
Should it be fx 1, 2?
Okay. Okay. It's -2 times x minus 1. Is that what you were saying? Yes. Okay. All right. Okay. And when you take the partial of this, you treat the y as a constant. That's a constant. So that is your slope in the x direction, which you could write, you don't have to, as -2x plus 2. Okay? Right? If you distribute that -2 across there, right? Okay. Now, here's what I was looking at and why I hesitated before. Another way you could do this is be 1 minus and then square that. That would be x squared minus 2x plus 1, right? Minus y squared minus 4y plus 4. If you squared those binomials. Well, if you took a derivative of this, it would be a minus 2x plus 2. Same thing. So, you could have squared it, or you could have left it just like that and did 2 times, or minus 2 times x minus 1, and that gives it to you. Okay? Now, let's go on and do your f sub y of xy. Always do it with respect to the variables first. And what would that be? Y minus 2, right? That's the 2 there. Okay? Got it? Okay. And you could write that, if you wanted to, you don't have to, as minus 2y plus 4. And if you did the derivative of this, it would be a minus 2y plus 4. Yeah. Same thing, just to check. So now it said, at this point. So f sub x at 1, 2. And again, you only use the xy values, not that z value. What would that be? Zero. And your f sub y at 1, 2 would be, say again? 0 again. So you must be at some extreme point, you might call it, where your derivative is 0. Well, sure you are. What did I just describe? This is your vertex. 1, 2, 1 is your vertex, because that's the point through which they're going. So sure enough, that's going to be a 0 slope at the top of that plane, right? No matter which way you go, okay? Anywhere else down the hill from there, you're going to have negative slopes. Everywhere else, but there it's going to be 0. And you can look at the picture and see that's the case too. All right. In fact, your picture shows those 2 horizontal lines. Okay. No matter how many variables are involved, partial derivatives can be interpreted as rates of change. But it's a rate of change with respect to one at a time, with the others held constant. So here is example 5. How are we doing time-wise? Oh, we got, what, about 10 minutes? I think we can get this one done. Okay. The area of a parallelogram with adjacent sides A and B, okay, and the included angle theta is given by this. The area is equal to the product of A times B times the sine of that angle theta. Okay? Now they show the picture. Both of you have books, right? One form or another. And when you look at those for people at home, if you were here, I'd draw it for you, but you're not here, so I don't know if you have a book or not. Okay? But the area here would be, wow. Okay. Here's your A, there's your B. So the base would be B times, now what you do is imagine that you have a vertical line here, and that cuts off part of this. Let's cut off here. And take this and move it over there, and now you've got a rectangle. This is heavy. Okay. All right. Take off this one and move it over here, and you've got a rectangle. Well, what's the height of that? That would be, the base is B, the height would be, that's the height is the opposite side, and the opposite side times the, that's your hypotenuse. So the opposite over hypotenuse would be the sine of the angle theta, right? Sine of theta is the opposite of hypotenuse. Some old hint, right? Remember? Okay? So that would be, to get the height then, it would be multiply A times the sine of theta. Goodness, that's heavy. Okay. And that gives you, so that's the height, so then you have the base, B times the height, A sine theta, that gives you AB sine theta. So there's how they got that, but that's how we get it. Okay? Now, the A part of this problem says, find the rate of change of the area, A, capital A, with respect to little a for A equal 10, B equal 20, and theta equal pi sixth. Okay? So the rate of change in the area with respect to your little a when A is equal to 10, B is equal to 20, and theta equal pi 6. All right. So rate of change would be dA. Okay? And it's with respect to A, so it's dA. I'm sorry. I'm so sorry. I'm still thinking ordinary derivatives. We're doing partial derivatives. Partial of A with respect to little a. Okay? And what would that be? You tell me. B. Okay. Yeah, but you see, I don't think, see, the theta is not changing any. So theta is a constant also. So don't take a derivative. That's just b sine theta. Okay? And this is when a is equal to 10, b is equal to 20, and theta is equal to pi 6, I believe it was, wasn't it? Yeah. Okay. So, what would that be then? B is equal to 20 times the sine of pi 6. What is the sine of pi 6? 1/2. So this would be 10. Okay? The rate of change of A with respect to theta this time. So now we're doing partial of A with respect to theta. Okay? Now what would that be? Now don't look at this one. Look back up here at the top here. What would that be? A little louder. A, B, times the cosine of theta. That time you do take it with respect to that because it says with respect to theta. Now we plug in those values. Oh boy, he just wanted to get marked here today, didn't he? All right. A big P for Justin. All right. You get to stay the last 4 minutes. Okay, good. Or is it 5? 5? Okay. All right, you get to stay 5 minutes then. I'll let you. Okay. Now we'll plug in those values, and that would be A is 10, B is 20, and this will be the cosine of pi 6. Okay? I know 10 times 20 is 200 times the, what is the cosine of pi 6? Anyone remember? Radical 3 over 2. Pi fourths would be radical 2 over 2. Okay? So this 2 will go into 200 100 times, so it'll be 100 times root 3. And you can look up and see what root 3 is. They don't. They just leave it there. 100 times root 3. All right. Does that make sense? That was example 5 on page 897. A and B parts. So what they sort of did was snuck one in with 3 variables in it. Here was your dependent variable, and then you had an A, B, and sine theta. Now, we didn't let B change any, but it could have. We let A change here and theta change here. So that was your thing. So while you weren't looking there, you just wanted 3 independent variables. 1 dependent variable, 3 independent variables. Okay. Now, do we have time for at least a slide? Partial derivatives as a function of 3 or more variables, which we just did, okay? The concept of a partial derivative can be extended naturally to functions of 3 or more independent variables. We already had 3 variables when we had 2 independent, 1 dependent. For instance, if W is equal to the function of X, Y, and Z, then there are 3 partial derivatives, each with respect to one of the independent variables. And then you hold the other 2 constants. So when you take the partial with 2, take the partial of f, hold y constant, or take the partial of y and hold x constant. When you have 3, partial of f with respect to x, you hold both y and z constant. And then the partial with respect to y would be holding x and z constant, and the partial with respect to z would be holding x and y constant. Okay? That is, to define the partial derivative of w with respect to x, consider y and z to be constants, differentiate only with respect to the x. Similar process for the other two with respect to y or z. Okay? Do we have time? Well, no, we don't have. Oh, here it is. Yeah, here are these descriptions here. The partial of w with respect to x would be f sub x, where alpha is equal to w. Okay? F sub x of x, y, z, and that would be the change with respect to x with y and z not changing. So if the limit is delta x approaches 0 of alpha of x plus delta x, yz minus alpha of x, y, z. So notice the y, z's don't change, only the x changes, and with respect to that amount of change. Partial w with respect to y, f sub y of x, y, and z. Then would be the limit as the delta y is going to 0 of alpha of x not changing, y plus delta y changing a little bit, z not changing, minus alpha of x, y, z, where only the y here is changed with respect to the amount of change of the y. And the same thing here. Partial w with respect to z would be f sub z, x, y, z, blah, blah, blah. Okay. Now, here's something else that happened this week. Well, let's go and finish this. I thought I was out of time, but I still have a minute or two.
Yeah, 2 minutes.
2 minutes? Okay. So in general, if f is some function of x1, x2, x3, x4, x5, up to x sub n independent variables, then there are n partial derivatives denoted by partial of f with respect to x of x of k, partial of f with respect to x of k of x1, x2, x3, all the way up to x of n, where k is 1 to n. To find the partial derivative with respect to one of those variables, hold all the other variables constant and only let that one change. Differentiate only with respect to the given variable. So that's what it says at the bottom of page 897. Now, I don't think we're going to have time to do example 6, are we? What do you think? Just a minute or something like that? Okay, here is the new change that happened Monday when nobody was here. They assigned a English or speech or something in another class to that classroom starting at 2, and that meant Dr. Bryant's physics class had to move in here. So that means we have 5 minutes, to get out of here. Normally they give us 15, because this class ends at 1:55, right? Then he has to start his class at 2. But frankly, I don't see the other class in that room, so he may be moving back there when he finds out. What's wrong?
Hey, if you got there, I was up for the discussing people that you can write about. You get me? Yeah, see, I took it like very close. I know you so well. It's like, I had to like that. Flowers, right? You did that summer? All right.
was going to give you some homework exercises, and we did run over, didn't we? Okay, so we'll start next time with example 6. So let me mark that here. And let me get this in place here. Oh, we almost finished 13.3, didn't we? Homework exercises include any of the odds 5 through 9. They're all at calcchat.com. Any of the odds, wow, there's a whole passel of these, 11 through 39. They're all at CalcChat. 13's at CalcView. Either 41 or 43, they're both at CalcChat. 41's at CalcView. Any of the odds 45 to 51, they're all at CalcChat. 45's at CalcView. Any of either 53 or 55 or both, they're both at CalcChat. 53's at CalcView. Any of the odds 57 to 61, they're all at CalcChat. 57's at CalcView. Any of the odds 63 to 67, they're both at all of them are at CalcChat. Any of the odds 69 to 75, they're all at CalcChat. And we'll stop there. Okay? All right. And we'll pick up the rest of those next time. Any questions? All right.